Section 3.3 is on rates of change in the natural sciences. So, a reminder to start, remember that a derivative can be interpreted as a rate of change. So, the instantaneous rate of change, in other words, is equal to the limit of the change in y and change over change in x as the change of x approaches what? Approaches 0. We want the change in x to be as small as possible. And in terms of our functions, we could say it's the limit of, okay, the change of y would be f of x2 minus f of x1, all divided by x2 minus x1 as x2 approaches x1. Okay, if that's confusing, probably is. All I'm saying here is if you had some function called f, and we wanted to know the instantaneous rate of change at this point here, let's call it x1. What we could do is we could take another point, x2, and we would want to get change in y over change of x. How would we get change of x? You do x2 minus x1, which is exactly what we have there. How would we get change of y? We take this y value. Well, what's that y value? It's f of x2. What's this y value? F of x1. So f of x2 minus f of x1. That's your change of y. x2 minus x1, we already said that's your change of x. And what we want to do though is we want to get this x2 as close to, darn it, we want this x2 to be as close to x1 as we possibly can. We want to shorten that distance. We want x2 to approach x1. Well, basically all that is probably a waste of time saying all that, because all that means is that the instantaneous rate of change is equal to the derivative of f when we use the x1 point, right? Put x1 into the derivative of f and you have the instantaneous rate of change at point x1. Alright, let's do a few examples. A spherical weather balloon is being inflated. Find the rate of change of the volume with respect to the radius when the radius is 10 centimeters. Okay, we're talking about a spherical weather balloon. So remember, a sphere is like a ball, and we're talking about the volume. What's the volume of a sphere? The volume is equal to 4/3 pi r cubed. This is volume in terms of r, right? This is the only unknown thing here is the r. Pi is just a number, it's just a constant, 3.141, blah, 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 blah. Okay, well, what we can do then, if we want to find the rate of change of the volume, is just take the derivative of this. Take v prime in terms of r. I can do that again if you want, put it in brackets. It's in terms of r. Take the derivative. So this whole 4/3 pi here is just like a constant amount. So we have r cubed. You're just going to use the power rule here. What's going to happen is that 3 is going to come down. It's going to multiply by the 4/3 pi. And then the r is now going to have an exponent of 2. I have no idea why I'm doing this in red, by the way. You can then cancel out the 3's. So what you're left with is 4 pi r squared. So if you wanted to know the rate of change of the volume for any particular radius, all you'd have to do is use this formula and plug the radius in right here. Well, for the question we're interested in, we're interested when the radius is 10. So you're going to find v prime of 10, which means 4 times pi times 10 squared. I'm putting the 10 right there. Well, 10 squared is 100 times 4 is 400 pi. And yes, we do like exact answers. You could multiply that if you want, get a decimal, but this is a beautiful answer. That's an exact answer. Now, what are the units? We're getting the rate of change of the volume. Well, volumes is in centimeters cubed because it says centimeters here. With respect to the radius, well, radius is just in centimeters. So this is your answer right here. Okay, question 2. The function n equals f of t is the number of individuals in a bacteria or animal population at time t. The change in colony size is change of n, f of t2 minus f of t1, over the time period t1 to t2. Therefore, find the average rate. Therefore, the average rate of growth equals and the instantaneous rate of growth equals. Well, to get the average rate of growth would be the change in the number of individuals, so change in number over change in time. And in order to get that, to get the change in number, you'd take the number at time 2, you'd subtract the number in time 1. Remember, this f is how we find the number, so I would plug those into f to figure out the number at time 2, plug into here to get the number in time 1, and we divide it by change in t. Well, change in t would be t2 minus t1. Okay, so that's for the average rate of growth. If we want the instantaneous rate of growth, you would be doing the same sort of thing, but you'd be making this change in t as small as possible. We'd want to take the limit of change of n over change of t as t approaches 0, which means you could find n prime, which is the derivative of n. So here we go, the population of a bacteria culture after t hours is given by this function. Find the rate of growth after 5 hours. We're looking for the instantaneous rate of growth, so all we have to do is get n prime. Just have to take the derivative. N prime equals, well, this is a constant, so it just equals 0. 200t, the derivative is 200, and 12t squared, power rule tells us it's 24t. So now we can plug any time we want into here. We want to plug 5 into there. So we're doing n prime of 5. We got 200 plus 24 times 5, which means 200 plus 120, which equals 320. Rate of growth, so this, we're talking about bacteria, it's 320 bacteria per hour. The description of these questions is way harder than the questions themselves, right? Confusing, not too bad. Confusing, not too bad. Okay, last one. The linear density, rho, this is the Greek, I think, letter rho. The linear density, rho, of a rod or piece of wire is defined as mass divided by unit length. If a rod is not homogeneous, which means constant or uniform, then its mass is measured by m equals a function of x from its left-hand end to a variable point x on the rod. Oh gosh, again, a pretty complicated question. Our description. So, for example, if we wanted to know from the left-hand end to some point, let's say here, x, if we wanted to know this mass right here, we would say that this part of the rod has mass equal to f of x. Now, what if we had other points over here? Let's call it x1 and x2. If we wanted to know the average density between those 2 points, what we would do is we'd look for the change in mass over the change in x, the change in the location on the rod, right? So in order to get the mass, we've said you use f of x for that. So you do f of x2 minus f of x1, and then you would divide that by x2 minus x1. If we want to know the density at any given point, this is like the instantaneous density, then we would say that it is equal to, there's rho again, is equal to the limit of change of m over change of x as change of x approaches 0, which means it would be equal to m prime, the derivative of m. So let's, for this question, find the average and the actual linear density. So first of all, the mass of the left hand, x meters of a rod, is f of x equals x squared. So this is the actual function for this one, for this rod. Find the average density of the part of the rod given by 2 is less than or equal to x is less than or equal to 2.3. So it's kind of like if this point right here was 2 meters from the end point, so from here to here is 2, and this one's 2.3 meters from there. Okay, I know it's real messy, but just give you an idea. And we want to know what's the average density of this bit in here. So how do we do that? We find f of x2 minus f of x1 over x2 minus x1. Okay, so let's do that. Change of m over change of x equals f of x2. Well, that means we plug x2, which is 2.3, into here. So we get 2.3 squared. Minus, now we plug 2 into f of x, so we get 2 squared. And then we subtract x2, which is 2.3, minus x1, which is 2. So 2.3 squared is 5.29. 2 squared is 4. We're going to divide that by 2.3 minus 2 is 0.3. So that's equal to 1.29 over 0.3, which is equal to 4.3 kilograms per meter. Now, what if we wanted to know not the average density from 2 to 2.3, but the instantaneous density, so to speak, right at that point 2? Well, then we would use this second formula here, which tells us we only have to take the derivative of m. Well, that's pretty nice, because we only have to take the derivative of this. Since m, remember, m is equal to f of x, which is equal to x squared, we just have to take the derivative of m, or the derivative of f, which equals 2x. Then we just have to plug 2 into there. And we get 2 times 2, which equals 4. Should be kind of ballpark the same as this, and it is, so I'm feeling pretty confident about our answer. And that's it. That's our answer. Okay, there you go. Another fairly quick lesson.